Thank you. So we are now switching the topic, and we shall use some today's lecture for discussing little bit about MESFETs. Before I go to what is MESFET, MESFET stands for metal semiconductor FET. So MESFET, okay, metal semiconductor FET. That oxide term is not there. MOSFET is metal oxide semiconductor. This simple metal semiconductor FET. Then why this MESFET? That has to be first understood. The main reason is the material gallium arsenide. Let me tell you the story. Traditionally silicon, started, the semiconductor industry started with germanium. Slowly it made a very smooth transition to silicon, and silicon dominated the entire industry for about 10 years. Okay. Thereafter, silicon started facing some challenge from another material called gallium arsenide. The reason is, gallium arsenide is a semiconductor which has a mobility, the electron mobility, which is much higher, about 8,000 centimeter square per volt second, whereas silicon mobility is only 1400, so many times more than that of silicon, and the mu p, of course, the same order. So far as mu p is concerned, there is no advantage, but so far as electrons are concerned, gallium arsenide definitely has a tremendous edge over silicon. But I have mentioned earlier in my previous classes that when you plot the velocity versus electric field, whereas for silicon the curve is like this, for gallium arsenide the curve is like this, which I indicated earlier, that yeah, the initial benefit of very high velocity for the given field in gallium arsenide is offset to a great extent at very high field when the velocities merge, almost come very close to each other. There is no special benefits for gallium arsenide at submicron, for submicron devices where the electric field is very, very high. That is why silicon, that with miniaturization, nobody could compete with silicon. It's still continuing. Silicon is the basic material with miniaturization. But in those days, when the technology, the dimension was several microns, the electric field, we are in this region of electric field, not here. Naturally, gallium arsenide had a tremendous edge over silicon. Being a wider band gap gallium arsenide band gap, you remember, is 1.4 electron volt, whereas silicon band gap is 1.1 electron volt. It is still wider band gap. Therefore, wider band gap has the inherent advantage of low leakage current, lower noise, and so on and so forth. Less temperature sensitivity, lower leakage current, low noise, high mobility means high speed, and all these advantages. Secondly, of course, it was a direct band gap semiconductor, which silicon was not. So in the same chip, you can make an LED and transistor and all other things. Optoelectronics and electronics could merge on the same chip, which is not possible in silicon. The silicon, still today, silicon's main bottleneck is that we cannot have an optoelectronics chip, an LED or laser made on silicon chip. Whereas gallium arsenide can do everything. On gallium arsenide, you can make a laser, a transistor, a VLSI chip, everything. Integrated optics, light switches, this, that, everything is possible on gallium arsenide. So all these considerations, after 10 years of development, it was found silicon started facing challenge from gallium arsenide. But in the meantime, there has been another very important development in silicon technology, that is MOSFET. When gallium arsenide people thought will beat silicon, then the technology was mainly bipolar, silicon bipolar transistor based circuits, ICs. And that way gallium arsenide is definitely superior because of the very high mobility and other better properties. But then MOSFET technology came. MOSFET technology was invented very long time ago, but it could not be commercially standardized because of various reasons, which or some I think you have been told in this class as well in other classes. But slowly the MOSFET technology became a reality, and in 60s and 70s particularly, MOSFET started growing like anything, and it became so important that the main thing in MOSFET, as you know, the power dissipation, high input impedance, dynamic memory, dynamic logic, and all this so far as VLSI implementation is concerned, logic implementation, it has tremendous various benefits. And there gallium arsenide found, it was gallium arsenide, almost some people suggested that gallium arsenide, I remember the papers, by 70s all ICs will be gallium arsenide ICs. I still remember. But things did not happen like that. Gallium arsenide started facing again challenge from silicon once the MOSFET came. And MOSFET came means entire ICs became LSI, VLSI and all this, which bipolar could not. But gallium arsenide there, they found there is a problem. It is very difficult to make gallium arsenide MOSFETs. MOSFET means you have to have a reliable gate dielectric, a very good passivating film. And the gate dielectric is not reliable, it will not work. And it was a very challenging task to grow a good quality dielectric film on gallium. Still the problem, some research things are going on, some commercial devices also people are trying to develop on gallium arsenide MOSFET. Till today, let me tell you, gallium arsenide could not find out ways how to have MOSFETs in gallium arsenide. And but gallium arsenide is a tremendously good material, very high mobility, etc. So people tried to find out intermediate ways, how to make better use of gallium arsenide. Should we be totally defeated to silicon? Because MOSFETs have come, silicon is doing so well, and gallium arsenide should stop in spite of its very good properties. So an intermediate solution came, and that is a MESFET. Let me tell you, that is MESFET. MESFET is nothing but a dignified version of JFET. Let me tell you what it is. So that's the story how MESFET came and became so important. Whenever we speak of MESFET, usually it is gallium arsenide MESFET, and sometimes therefore such devices are also called GaAs-FET, GaAs-FET. MESFET sometimes are also referred to as GaAs-FETs. We call it GaAs-FETs because it is mostly the material is gallium arsenide and never silicon. Nobody will like to use silicon for MESFET because already MOSFETs are there. These are some very basic things. Many people do not know about it. But this should be remembered. Nobody, have you heard anybody that silicon MESFET? Silicon JFETs are okay, but never MESFETs. But whenever we speak of gallium arsenide, it is MESFET or BJTs or HBTs. Gallium arsenide BJTs, gallium arsenide HBTs, gallium arsenide MESFETs, and gallium arsenide other devices like gallium arsenide, say solar cells, gallium arsenide CCDs, gallium arsenide detectors, gallium arsenide lasers, gallium arsenide, say for example, gallium arsenide other kind of devices which are so important with gallium arsenide is different range of optoelectronics and millimeters, impact diodes, gun diodes, this, that, all these things are gallium arsenide based. Now, what is MESFET? It is nothing but a JFET, little bit different. It's a MOSFET kind of device with a Schottky gate. A typical gallium arsenide MESFET looks like this. You know the advantage, one advantage of gallium arsenide which silicon does not have, that is as follows. We can get gallium arsenide in a very high resistivity form. Silicon, what is the band gap of silicon? 1.1 electron volt, band gap of gallium arsenide 1.4 electron volt. Intrinsic resistivity of silicon is very high. Very high. But in practice, it is very difficult to get silicon wafers which has resistivity higher than 1000 ohm centimeter in practice because of imperfections, some doping which automatically incorporated, etc. Getting silicon wafers of resistivity higher than 1000 ohm centimeter is very, very difficult. In fact, 1000 ohm centimeter silicon is very expensive. Up to 100 ohm centimeter silicon is not that expensive. But as soon as you exceed that 100 ohm and it goes to 1000, maximum 2000 ohm centimeter, silicon becomes very, very expensive. Whereas gallium arsenide, it is easy to get a gallium arsenide wafer with a resistivity of 10 to the power 8 ohm centimeter. This is called semi-insulating gallium arsenide. So what is normally done, we use a Si gallium arsenide as a substrate with a resistivity of 10 to the power 8 ohm centimeter. In fact, how it is done is, if you take pure gallium arsenide, though it is, you are assuming intrinsic gallium arsenide should have a very high resistivity, but in practice due to the impurities, the resistivity will fall. But if you dope it with chromium and some impurity levels are introduced, they compensate the semiconductor by certain mechanism. And it is not difficult to achieve a resistivity as high as 10 to the power 8 ohm centimeter in gallium arsenide, which is highly advantageous. Because in that case, automatically you are getting a substrate which is practically a good insulator. 10 to the power 8 ohm centimeter is a reasonably good insulator. So electrical isolation will be very good. This is an interesting thing. So if you start with a semi-insulating gallium arsenide like this substrate, then do the following. You implant some, that what they do, there is a channel region and there is source and drain regions. So you implant silicon. Usually silicon is implanted, or selenium, very typical, sulfur, silicon, selenium, sulfur. If you implant on gallium arsenide, it is converted into an N-type layer because they call it 6 group to 3,5 compound. If it is doped with group 6 impurity, it becomes N-type. Silicon, but silicon is a different thing. Silicon it is found to have a very effective N-type impurity for gallium arsenide. Otherwise, selenium, sulfur, etc. were previously used. You implant them, but you have 2 implantations here. These are very heavy dose implantation and higher energy. Whereas in this region, you have very light implant at a low energy. So that you have an N-type layer of relatively low conductivity here, and on either side you have very heavily doped regions. Then what you do, you can have certain kind of many things. People normally use silicon nitride. Gallium arsenide technology is quite different from silicon technology. In silicon, you remember that these oxides could be grown simply by treating oxygen or water atmosphere, called oxidation, which is not possible for gallium arsenide. You have to deposit a film. Typically, silicon nitride is very popular for gallium arsenide. Or PSG glass, sometimes oxide, etc. But silicon nitride is very popular. So you deposit silicon nitride and pattern it in this form. This will work as a passivant as well as a mask. Then you use here a metal. That means you deposit a metal film and pattern it on the source and drain, and these metal film should be so selected that they act as ohmic contact after anneal. So this is source and this is drain, and the metal is typically gold, germanium, nickel alloy, ohmic contact. And on the channel region, you deposit another material which behaves as a good Schottky contact on silicon, on gallium arsenide, N-type gallium arsenide. There are many Schottky materials. Typically, it may be titanium, platinum, gold, Schottky. So what is the difference between this structure and the MOSFET structure? If you compare, firstly, forget about the semi-insulating. Normally in MOSFET is P-type, then you have N plus, N plus. But this is semi-insulating gallium arsenide. As an advantage, you have got a very high degree of isolation, automatic. There is no need of SOI or kind of technology in gallium. Gallium arsenide has that tremendous advantage in that aspect, let me tell you. Whereas, then over the channel region, you have an N region. So basically, this will be a normally on device. This is a JFET type of device, because N plus and the channel consisting of N. So the canal will conduct when gate potential is 0. Okay, and the gate is to be having, here you cannot use oxide, a good dielectric is not possible. Either you can have a JFET, that I'll show you. You can have a JFET here, that means in this region you could have a P plus diffuse region, and in that case it could have become a JFET. But instead of have a JFET, you can have a Schottky contact here. No oxide or dielectric. There is a metal gate, but this metal gate is Schottky gate. And the Schottky gate is, if it is reverse biased, it behaves very similar to the PN junction. A depletion layer, reverse bias, a good Schottky barrier diode, in the reverse bias provides a very little leakage current, and around it there is a depletion layer. So the same thing will happen. If you reverse bias the junction, this Schottky diode, there will be a depletion layer which will choke off, which will pinch off the channel, and the current will stop flowing at the voltage which is called pinch off voltage. At the voltage which is called pinch off voltage. So you are having a very similar structure like MOSFET, almost looking like MOSFET. And it is also a FET which will give you a current voltage characteristic very similar to MOSFET or JFET, looking like this. but this may be for Vg is equal to 0 volt, and this may be for Vg is equal to Vp, some negative voltage to be applied to negative or positive voltage. To pinch up the channel, the gate voltage should be negative or positive? Negative voltage. So you have to apply a negative voltage. Vp may be, say, minus 5 volt or minus 3 volt, depending on the channel thickness. The thickness of this channel. Vp may be minus 5 volt, minus 3 volt, minus 1 volt. Okay? And you get a current flow, and then this is for Vg greater than 0, and this is for Vg less than 0. Advantage of this structure as compared to MOSFET is, suppose this channel length is suppose 1 micron or 2 micron. 2 micron technology is a rather very simple technology to put. Suppose, even our laboratory with certain modifications can go for 2 micron technology. It's very simple compared to the deep submicron or submicron technology of CMOS. So if you have a 2 micron technology, you can achieve a speed which is as good as that of an N-MOSFET with, say, maybe 0.2 micron, 0.3 micron technology, 0.5 micron technology, because your mobility is extremely high. Your mobility is extremely high. Do you agree with me fully, or do you have something in your mind that you should not properly correct? I say that if for some channel length which is not too short, typically MOSFET, the JFET channel length is around 1 micron. Let me tell you, in practice, JFETs which are available in the market, the channel length is about 1 micron. But 1 micron technology, let me tell you, from lithography point of view, is rather simple compared to today's submicron or deep submicron technology. So I say that when it is 1 micron or 2 micron, you get the same order of delay, same order of speed as compared to a N-MOSFET of very small dimension. Do you fully agree with me, or you have some reservations with this statement? In fact, we do not get, that is what was revealed afterward. It was found that it is not only the this delay, the transient delay along the channel, but also the charging time of the capacitors, they become very important. And the capacitance of these junctions, which account for the charging times of the pulses, they have to be reduced. But with scaling, that can be, because with this kind of, when the structure is big, these capacitances are also big. Though the intrinsic delay here is very short because of the high mobility, but that is offset to a great extent by the bigger capacitances. So gallium arsenide MESFET technology also requires scaling down. So if you want to be competitive with silicon, you have to also scale down the whole thing. Otherwise, it is not possible. But while scaling down, you find that you are now in this regime, not here. So the benefit which you gained initially, that is also offset to a great extent. So silicon people are very happy that yes, gallium arsenide came and became a challenge, but again it slowly, but still it is very important. So gallium arsenide is scaled down technology, the special things. One can make gallium arsenide FETs which are much higher speed conventionally as compared to silicon. But silicon people is also working very hard. Germanium gallium, germanium silicon structure, heterojunction, silicon carbide, and all these heterostructures, they are pushing the silicon frequencies also to hundreds of gigahertz range. I'm coming to that afterward. Please repeat.
Gallium arsenide.
SOI gallium arsenide usually not required because of the semi-insulating gallium arsenide advantage. That is why nobody thought of. SOI gallium arsenide is going to be very complicated. Except gallium arsenide is a two-element semiconductor, na? Bi-element. When you hit, arsenic tries to come out. So that there are many things which you have to do to protect the stoichiometry of gallium arsenide to retain its perfectness. Silicon, those drawbacks are not there. Silicon is such a material, that you suddenly dip it in hot water, drag it out, nothing, but you just take many other material, you dip it boiling water, it will instantaneously it will crack because of thermal expansion mismatch. Silicon is very rugged. Quartz, silicon, these are very, very rugged materials. But then I mentioned earlier, what is the kind of MESFET device? Basically, therefore, MESFET is a depletion mode, na? MESFET is a depletion mode device. Is it very desirable? I have mentioned so many times in the class, when you design a logic circuit, do you think that depletion mode MOSFETs or MESFETs or MOSFETs, both MESFET or MOSFET does not matter, are highly desirable? Because of that, because here the gate voltage requirement is negative, 0 to negative for switching it off, whereas the drain voltage is positive. So the output of this, of an inverter, cannot be directly connected to the input of another inverter. Because output of this device will be a positive swing, na? 0 to VDD. VDD is positive. Whereas to switch it on and off, we need negative voltage. So there is no input-output DC compatibility of depletion mode devices. Therefore, we need enhancement mode device. But unfortunately, by nature, the MESFET is a depletion mode device. But there are some means to convert them in. One technique was simply a MESFET technology. What is done is simply a JFET technology. SI stands for semi-insulating. Have I told you? SI stands for semi-insulating. SI gallium arsenide. Then you have a structure like this. So this technique is as follows. You take a silicon semi-insulating gallium arsenide substrate on which you epitaxially grow. This is a N-type silicon, N-type gallium arsenide epitaxial film. You grow an N-type gallium arsenide epitaxial layer or epitaxial film, and normally this N-type is usually silicon or germanium doped. Okay. While growing the epi layer, you also incorporate at a steady rate some silicon atoms or selenium atoms, not germanium, selenium atoms, or zinc, sulfur atoms to make it N-type. Silicon is very popular today for various reasons. Then you have a P plus doped region at the center. Usually it is zinc or beryllium doped. P plus doping is done by zinc or beryllium. Then at the two ends, you have N plus doping by again silicon, heavy dose implantation. This is all done by implantation, not by diffusion. Implantation annealing, diffusion is avoided. Then you have, as before, now there is no need of Schottky contact. This is a MESFET. This, though I am calling MESFET, basically it is a GFET. It's a GFET, but with an extremely thin channel. So these contacts are all ohmic contacts. So you can use gold, germanium, nickel alloy for ohmic contact. As before I indicated, the ohmic contacts here were made using gold, germanium, nickel alloy, whereas Schottky you can use different other material. For example, one such material was titanium, platinum, gold. So in this case, these are all ohmic contacts. Okay. Now, what is going to happen because of the extremely thin channel, because this thickness is very small, has to be properly designed. And the doping of the N region should not be that small. It should be relatively, that should not be high. It should be small enough. Typically around 10 to the 15. 10 to the 15. So what will happen? If you do not apply any gate body, Vg is equal to 0. If Vg is equal to 0, what will be the value of ID? You see that this is an N-type layer. N plus means ohmic contact. The channel is open. Channel is just continuous. Current should flow. But current, I want that current should not flow. So that is an enhancement mode device. How? Because the channel is so thin that the depletion layer around it, due to the built-in potential, chokes the channel. Due to the built-in potential of the PN junction, that chokes the channel, keeps the channel pinched off. So ID will be equal to 0. Because the channel thickness is very small. This will not happen if channel thickness is large. How to turn the device on? You have to forward bias this channel. But it is a mess, it is a FET. Please remember, as soon as I am using the terminology FET, I should not use much current to turn it on or off. It is a field effect device. So, I must respect my IG versus VG plot, and forward bias it looks like this. This is the cut-in voltage. My voltage, the forward bias should never exceed the cut-in voltage. If the forward bias by chance exceeds the cut-in voltage, the current will be large, and you get all. In fact, it will not. It will be very. The device will be. In fact, in many cases, such JFETs or MESFETs, if you forward bias the junction, the device may be burnt off. So your Vg should be less than, considerably less than V gamma. Therefore, logic swing will be very small. It is an enhancement mode device because when Vg is 0, Id is 0, and when you apply a small positive voltage at the gate, is small. How much small? Typically for gallium arsenide, the this turn-on voltage, Schottky voltage, this voltage is around a volt. You should keep within 0.8 volt, 0.7 volt. Typical logic swing should be 0 to 0.7, 0.8 volt. This is important. But then, you know that if it is a 5 volt or 10 volt circuit, normally gallium arsenide circuit is maybe below 5 volt, still not that developed. 5 volt circuit, and if it is a 0.6 volt, what is the logic swing in ECL gates? Logic swing, VOH minus VOL, 0.6 volt, 0.6, 0.7 volt. Same, very small, that is a drawback. You know, the levels are, but the logic swing is very small in ECL gate, in I2L logic and all these things. But they are very high speed. But basically this is a JFET, please remember. This is not a MESFET in that sense. It is an enhancement mode device. It is an enhancement mode device. It is also possible to realize enhancement mode MESFET, and the structure looks like this. Typically, say tungsten silicide gate, very popular. This is Schottky. These are ohmic contacts. So these two are ohmic contacts, the same gold, germanium, nickel alloy you can use for the contacts. But here, this region is not only a very low doped. This is semi-insulating gallium arsenide. It should have a relatively low doping, around 15 or less. Thickness should be very precisely controlled, maybe 1000 angstrom, 2000 angstrom, like this. Then you have a Schottky gate here. Here also the same thing. When Vg is equal to 0, Id is 0 because the channel thickness is small. For what reason? The channel thickness is very small and channel doping is also relatively small. So you have to precisely control the channel thickness and channel doping so that under normal condition when Vg is equal to 0, the channel is choked off by the depletion, due to the depletion layer as a result of the built-in potential of the channel, Schottky barrier, built-in potential in the semiconductor side of the Schottky barrier. Only by applying a forward bias you can turn it on. Therefore, what is needed here? What is the special requirements for such enhancement mode MESFET? The Schottky barrier height of this metal should be relatively high. So the work function, you have to look for a very high work function material. Tungsten is quite common, but tungsten silicide is a better material. And it will give you a Schottky barrier of around 0.9 volt. Schottky barrier of around, cut-in voltage around that. So Schottky barrier, so you can safely work up to about 0.8, 0.9 volt. Swing, the voltage swing can go to about 0.8 to 0.9 volt. Voltage swing requirement is the Schottky metal must have a high work function. That is why I have selected tungsten silicide. It is a typical material for this. This kind of devices, the MESFETs, which is normally depletion mode type, they work very well under depletion mode condition. Enhancement mode is required for circuit requirements, which I have repeatedly told you. Driver should be enhancement mode device. Therefore, modern MESFET logic, called GaAs logic they call it, they are used normally for special optical amplifiers, etc. On the front in the modulation circuit of fiber optic amplifier, fiber optic control circuits, and different other applications they are used. And there, you know that the this enhancement mode MOSFET is that MESFET is the requirement of today for so that you can have variety of circuits just like MOSFET circuit. You can have dynamic logic also. The only thing is this dynamic logic will work only at a very high frequency. Why? A dynamic logic using MESFET technology has to work, normally will work at a higher clocking rates, higher clock frequencies than those using silicon MOSFETs. Why? Because the leakage resistance, you cannot have the kind of leakage resistance which silicon MOSFETs give you, which is hundreds of mega ohm, and it will be only hundreds of kilo ohms only. It will drop from hundreds of mega ohms to hundreds of kilo ohm in this case. About a mega ohm or less than mega ohm, around 500 kilo ohm, 200 kilo ohm kind of thing. Enhancement mode MESFET of this kind of structure will give you resistance of the order of 500 kilo ohm, 100, 200 kilo ohm like this. So you cannot expect that such dynamic logics will work at a very low clock rates, which is the beauty of silicon logics. There is one other version of this MESFET which came, that is what is known as permeable based transistors. This is basically a vertical MESFET. It looks like this. What is the structure? This is a MESFET, at the same time this is a BJT. Very similar. Therefore, some people this can be visualized as a MESFET or can be visualized as a BJT. That's why the names collector synonymous with drain, emitter synonymous with source, base synonymous with gate. The structure you carefully see. We have an N plus gallium arsenide substrate on which you grow N-type gallium arsenide up to this distance, up to this thickness by epitaxial technique, on which you deposit titanium, usually tungsten gates, something like CCD array. Okay, and along with the tungsten, we grow another N-type epitaxial film. It can be shown by a process called lateral epitaxy. It is possible to grow an epitaxial film surrounding these tungsten electrodes, which are embedded. That is why the structure is vertical. These tungsten electrodes are, and there must be some access outside. You should have the connectivity. You have to design in such a way that you can connect these gates. Then what is going to happen? You know that this gate, the tungsten N gallium arsenide, behave as Schottky diode. And because of the, that you can design it in such a way that it will behave as either as an enhancement mode device or depletion mode device, depending on the spacing of the grids. It is very similar to triode, pentode. Have you studied little bit vacuum electronics, triode, pentode, grid structure? Very similar to that. So you interplaced a grid of tungsten material, tungsten electrodes, which are separated, but spacing is adjustable in your design. And suppose initially without any gate potential, all these depletion layer they merge due to the built-in potential. There will be no current flow. But if the spacing is such that in built-in potential there is still a gap present here, the current will flow vertically. Okay? And if you reverse bias this junction, the depletion layer will widen and the current flow will be stopped. And in the case of enhancement mode device, the spacing is very small. If you forward bias the junction, the current will flow. That's the greatness about it. This is a very complicated structure, and it was very interesting academically, but did not come to be a very successful one commercially. But it has certain merit. Can you tell me what is the merit? Because the structure is vertical, you can have these thicknesses extremely small. Otherwise, gallium arsenide, which is horizontal structure, the only technique of defining distances are by lithography. But it is vertical layer. The epitaxial films can be grown to very small thickness. Therefore, one can achieve very high speed. People reported some FT value which is around 200 gigahertz using this kind of structure. Very innovative, excellent, academically attractive structure. Excellent structure, academically attractive. Lot of publications, lot of models, this, that came because it's a beautiful structure. But commercially that was not so much acceptable because of the complications involved.